Good afternoon. So, what topic did we discuss in our last lecture? So, we discussed policy iteration, and we proved that policy iteration is a contraction mapping, right? So, what is the use of that? What is the use of proving that policy iteration is a contraction mapping? And I think we briefly introduced what is value iteration. So, we'll discuss that again. And in today's class, what we'll do is so we'll also look at how many iterations do you need in a policy iteration algorithm for it to converge, right? So it's an iterative algorithm which we are doing using Bellman expectation of equation. So we'll try to understand how many iterations will be required, right? Uh, so that is one topic which we'll cover, and then we'll cover a few variants of these two algorithms, like policy iteration and value iteration are two algorithms. We'll discuss few variants of them. Okay. Um, then what we'll do is, in, till now we have been assuming that we know the dynamics of the MDP, right? We know that the transition probability matrix and the expected reward for every action in every state. So if we do not know this model dynamics of the MDP, how do we solve these problems? How do we find optimal policy if we do not know the dynamics of the MDP? Like that's what we did in the bandits case, right? We did not assume that we know the true means of the arms. We were trying out few arms and then we found out roughly which is a good arm and then we played according to that. So that means there we did not know the dynamics in the sense that we don't know the reward distribution. Similarly, in the MDP setting, if we do not know the reward distributions and the transition probabilities, how should we solve for the optimal policy? So that's what is mainly the reinforcement learning. Because if you already know the dynamics of the MDP, then it's like solving some particular optimization problem. So there is no machine learning as such in a sense. You're not having any data that you're collecting or you're not doing anything. You are just solving some particular optimization problem. But when we do not know the dynamics of the MDP, then you have to get some samples and then based on some estimates, you have to decide which action to take, etc., which is what the core RL problem is. Okay. So we'll look at the model free, that's called model free setting, or you can think of it as model free RL. Okay. Where we do not know the dynamics of the MDP. Okay. Mm. When dynamics are how to solve it, MDP dynamics are not known. Okay. So like roughly this is what we'll discuss today. So can you recall what is policy iteration algorithm? Do you remember what is policy iteration algorithm? So what did we do in policy iteration algorithm? Yeah, you start from some arbitrary policy pi naught. You evaluate how good is that policy. So for that we use policy evaluation. Then what will we get? We get v pi naught. And after that, what do we do? So we do policy improvement, which will give us 5-1. How we are doing policy improvement? How we are doing policy improvement? 5-1 of S is argmax over A, which is the greedy improvement step. Q pi naught of S comma A, right? This is how we were doing the policy improvement. So we get a new policy, then again evaluate that new policy, then again improve that policy. So if you do this till pi t plus 1 equal to pi t, then we would have reached an optimal policy. Okay. And how are we doing policy evaluation? So given a policy pi, how do we find V pi? What do we know? Yeah, we use the Bellman expectation equation. What is Bellman expectation equation? Right. So this is the Bellman expectation equation. How do we use this equation to find V pi naught? One way is to use this equation and solve it in Ax equal to B form. But as I mentioned, taking inverse for a large state space may be difficult. Because of that, we came up with an iterative algorithm, right? What was that iterative algorithm? You start with some arbitrary V naught, which and then you keep applying this iterative form V naught. So you just this is Bellman expectation equation. How we are doing this is Vk plus 1, we'll take it as so we'll just recursively starting with some arbitrary V naught, we'll just recursively apply this. Uh, we just recursively apply this equation till Vk plus 1 becomes very close to Vk or equals to Vk or becomes very close to Vk. Okay. So I don't know how many of you have looked at the assignment. So the assignment is about coding this algorithm. Right? I think the deadline is this coming Sunday. So you have to just so this is you will be given R pi and you will be given P pi. You have to just apply this equation iteratively till you converge. Then you will get how to find a particular value of a policy, of a given policy. Then after that, you have to just improve the algorithm, like improve the policy using this update. And you keep doing this till pi t plus 1 becomes pi t. So we have given a particular MDP environment as a IPy notebook format. You can just code these two parts like policy evaluation and policy improvement. Okay. So if you keep doing that iteratively, you get 5 star. So this is about the policy iteration. So what did we prove about this equation in the last class? About this equation, what did we prove? Like if Vk plus 1 equals to Vk, then we know that it is equal to V pi naught because V pi naught satisfies that equation. But we were not sure whether such a equation will converge to V pi naught. If it converges, then we are sure that the value that it will converge to will be equal to V pi naught. But we don't know whether it will converge, right? If you remember, I gave some examples. Uh, so So how do we prove that some 6-point iteration like this will converge? What techniques did we study? To Banach-Fitts point theorem. Do you remember? So if we can show that a function from Rn to Rn, if there is a function which takes a vector in Rn and gives you another vector in Rn, if it's a contraction mapping, that is, if you take two vectors in that space before applying the function and after applying the function, if the distance between them decreases, then we call it a contraction mapping. So that was one condition. And what are the conditions we had? There were three conditions, right? So it should be a complete metric space. That was one condition. Yeah, what was a complete metric space? What was the definition? Do you remember? Yeah, any convergent sequence. If you take any convergent sequence in your vector space, the limit of that sequence should also be present in the same space. So then you call it a complete metric space, right? So there was one more condition. So if we just showed that this particular mapping is a contraction mapping. So what did we particularly show? Like if we call this as f pi of v, if we define this as f pi of v, which is r pi plus gamma p pi into v. It's a function in Rn, like which will take a n-dimensional vector and give you another n-dimensional vector. For this, we have shown that this particular function is a contraction mapping. So if you take, so that's why this iteration, that's why this iteration will converge to uh, v pi naught. Okay, v pi. So now we are also in this class. Will not all in the last class we already showed that this iteration will converge because it's a contraction mapping. But we also want to understand how many times you have to repeat this equation iteratively so that vk plus 1 is close to v pi. We want it to converge to v pi, right? So for what k will it converge to v pi, or how many iterations do we need so that it will converge to v pi? So that's what we'll try to understand in this class. So what we'll show is, uh, if you want, let's say at some iteration after k iteration, let's say you got a vector vk plus 1. We want to understand how close is this vector to what is the vector of interest? What should it converge to? V pi, right? So what is the distance between vk plus 1 comma v pi? This is what we are interested in, right? So let's say you want this to be less than some epsilon for some small value of epsilon. We want this to be close to v pi, right? We want vk to get closer and closer to v pi, right? So let's say I want this vk plus 1 to be uh, not that not deviate from v pi by more than epsilon, right? You want to be within an epsilon region about around v pi. How many, what for what value of k will this equation hold true? So I'll say I'll pick some epsilon, let's say 10 power minus 3. So what should be my v k? So how many times I should run this? How many times I should run this iteration so that my vk is, let's say, 10 power minus 3 closer to v pi. So that's the question we are trying to understand in this class. Okay, is the question, is the setup clear? We know that vk tends to v pi as k tends to infinity, that we know. But if you want a guarantee that vk is within epsilon of v pi, if you want that guarantee, how many minimum number of iterations or how many iterations are sufficient to ensure this guarantee? Okay, that's what we will try to understand. How many iterations required to ensure this? Okay, that's what we try to understand. or how many iterations are sufficient. So this is where the contraction mapping also comes into help for us to prove this particular, like to obtain some sufficient conditions on K. The contraction mapping will help us here. So, so first of all, to measure the distance between, so do you know, all of you know the triangle inequality, right? That is the distance between any two points is like if you have some, let's say some number of points, if you want to measure the distance between these 2 points, that distance will be lesser than the distance if you come across this particular path, let's say the red path, if you measure the distance, and if you measure the distance in this green path, the green path distance should be lesser than the red path distance. That's what triangle inequality says, right? So if you, so similar, we'll try to think of this as vk plus 1, let's say. Uh, so let's say this is some vector vk plus 1. This is some point, and we are trying to understand how far is that from, let's say, another point v pi. Now, what I'm going to do is I'm going to bound this distance using some other distances. Okay. Like what I'll do is I'll take these points as vk plus 2, vk plus 3, so on till infinity. Okay. So I know that vk plus vk as k tends to infinity will be equal to what? Vk as k tends to infinity is v pi, right? So if I look at all these points, vk plus 1, vk plus 2, vk plus 3, so on till infinity, then that path will lead me to v pi, right? Because as k tends to infinity, I'll reach v pi. Is it clear? So this path is vk plus 2, vk plus 3, vk plus 4, so on till infinity. So that particular path will reach me to v pi. This is that's the red path, and this is the green path. Now this distance due to triangle inequality will be less than or equal to what? Distance between vk plus 1 comma vk plus 2 plus distance between vk plus 2 comma vk plus 3 plus so on, right? Because that's the distance of the red path. So I am just writing that the distance of the green path is less than the distance of the red path. This is because since vk tends to v pi as k tends to infinity. This is the reason which, okay. Now, what is, what is, can we write vk plus 2 in terms of vk plus 1? What is vk plus 2? F pi of vk plus 1, right? That's how we are deciding, right? What is our iteration? This is our iteration, right? Vk plus 1 equal to f pi of vk. Correct? That's what we are iterating over, right? So now we know that uh, this is equal to d of so can I write it like this? This is equal to d of vk plus 1 comma vk plus 2 plus d of f pi of vk plus 1 comma f pi of vk plus 2 plus so on, right? I just now From the contraction mapping, can we get anything for this term? Can we get a bound for this term? What does contraction mapping tell us? Before applying F, uh, it will give us a some bound, right? The distance after applying F between any 2 points is less than or equal to the distance before applying F. That's what contraction mapping gave us, right? You take any 2 points in that space, you measure the distance before applying F, you measure the distance after applying F. The distance after applying F will be lesser. That's what the contraction property is giving us. So that means this distance will be what did we prove exactly? We did not just prove less than, right? We proved less than or equal to some gamma times the previous thing, right? So this is less than or equal to T of Vk plus 1 comma Vk plus 2. If you just refer to your previous class lecture, we have shown that this is less than or equal to, right? Gamma is the discount factor, which is a number between 0 and 1. Okay, same number. So we proved that F is a contraction mapping with the gamma as this parameter. Okay. So similarly, the remaining terms, the next term can also be written as gamma into dk plus 2 comma vk plus 2 comma vk plus 3. That I can again write it as gamma square into this thing. So if I do that properly, what will I get? This is less than or equal to what? Sigma over I equal to 1 to infinity d of I equal to k to infinity vi plus 1 comma, right? So this is less than or equal to, or I can just directly write this. That's okay. Is less than or equal to gamma power I into d of vk plus 1. Uh, what do I get? What will be my value here? Will be, huh? So this will be I plus 1 comma I minus something, right? Hmm. Right. So I'm just writing this expression in this way. So here I would have got gamma square into d of vk plus 1 comma vk plus 2 plus so on. Okay. So this is so this thing I can bring out. What will I be left with? This is right. Huh? Where one upon? Okay. Yeah. So we are able to relate the distance between vk plus 1 and v pi uh, in terms of our current distance, right? So if you want the final distance to be less than or equal to epsilon, we know where the current distance should be, right? This is what is this d of vk plus 1 comma v pi, right? So this is less than or equal to this, right? The distance between vk plus 1 is less than or equal to this. We got this, right? So now what is it we are interested in? We are interested in we want to stop it since it is uh, less than uh, epsilon, right? If you want this to be less than epsilon, we can understand what should be the distance between vk plus 1 and vk plus 2, correct? If you want this to be less than epsilon, you just stop at a point where you have some vk plus 1, you just compute vk plus 2 and see whether the distance between them is less than or equal to epsilon into 1 minus gamma, right? We want dk d of vk plus 1 comma v pi to be less than or equal to epsilon. So stop when dvk plus 1 comma dvk plus 2 is less than or equal to epsilon into 1 minus gamma. Okay. So you keep repeatedly applying this vk plus 1 equal to f of vk till the difference between two successive vectors vk plus 1 and vk is less than or equal to epsilon into 1 minus gamma. You decide how close you want your final answer to be, right? If you want, if you can tolerate epsilon of let's say 10 power minus 6, you take epsilon equal to 10 power minus 6. You already know gamma from your NDP specification. So you know epsilon because epsilon is something which you are deciding based on how much accurately you want to compute the V pi. So you fit some epsilon. You already know gamma from your MDP formulation. Now you just keep applying fk plus f vk plus 1 equal to f pi of vk till the difference between two successive vectors that you get is less than or equal to that number. That will give you a stopping criteria. Okay, when can you stop your algorithm so that you reach your desired accuracy? Okay. Any doubts in this proof? No, this is a sufficient condition. This is not a necessary condition. So if you if you do at least this much, you are guaranteed to be less than or equal. It could be zero. That difference could be zero. But you won't get if you take epsilon equal to zero, you won't get a number which is applicable for all the MDPs. So this is we are not making any assumption on which MDP you are talking about, right? Like there could be some worst case, corner case MDPs. For that also the proof should work. So this is just a sufficient condition. In some examples, maybe after a few iterations, you might see VK plus 1 equal to VK. Then you can stop, right? But let's say VK plus 1 is not equal to VK. How do you decide whether to stop there or not? Because you can only measure the distance between VK plus 1 and VK. You cannot tell what will be the difference between VK plus 1 and V pi. That's what you care about, right? VK plus 1 and VK difference, you know. But you want to be sure about how close I am to the value which I want to go to. So this is just giving a relation between the distance between VK and V5, right? So based on two successive vectors, you are able to understand how close you are to the actual limit. Okay. Any doubts at this point? Fine. So it's just an iterative algorithm. If you meet the stopping criteria, you can stop your algorithm, and it will ensure that you are at least epsilon closer to the limit. Okay. So this is about policy iteration and the convergence of policy evaluation and how many steps you have to run policy evaluation, etc. Now we look at value iteration a little bit closely. So what did I tell you about value iteration? Do you remember? So what is the value iteration algorithm? So I think I just gave you a quick intro saying that right now you are starting with some arbitrary policy pi naught. Then you are evaluating that to get v pi naught. Then you are improving to get pi 1. And this is a iterative step, right? Policy evaluation we are doing using v pi vk plus 1 equal to fi of vk, which is an iterative algorithm. So like we just understood how many iterations are required to ensure that vk is closer to v pi. So let's say I don't want to run for this many iterations. I'll just run for one iteration. I'll start with some arbitrary v naught. I'll just apply f5 once, and then whatever v I get, I'll just improve the policy with that. Okay. So I'll just run policy evaluation only for one step, one iteration, and then I'll get some roughly some v pi naught, some approximation for my v pi naught because it's run only once. You might not guarantee that it's epsilon close or anything. But I'll just treat that as my v pi naught, and I'll just improve. I'll just do policy improvement on that and get pi 1. Again, I'll just evaluate only for once using policy evaluation, and then again I'll improve. So this is what is called value iteration algorithm. When you listen it to the first time, it looks like it might not work because you're not running policy evaluation till your epsilon close or something. You're just running it once. But we can show that this will converge to optimal policy. We'll just see why it will converge to optimal policy. Run policy evaluation only for one iteration and apply and improve, like and apply policy improvement. Okay, that's what roughly value iteration means. So, so let me show you why that's the case. So let's say I started with some policy pi naught and I just applied f5 on it once. I start with some arbitrary v naught and apply f5 once. Okay, so I'll get some v naught, let's say, after applying f5. So what will I do after applying v f5 once? I'll have to improve that policy, right? So what is the policy improvement step? So let's say started after applying policy evaluation only once, let's say you got a V naught. Now you are trying to improve. Just treat that as equal to your V pi naught. Just treat your V naught is equal to V pi naught and apply policy improvement. Okay. So what is policy improvement? What is the policy improvement step? Argmatch over A Q pi naught of S comma A, right? So what is Q pi naught of S comma A in terms of V pi? So you have to be very comfortable with these equations. Okay. Actually, in fact, with this lecture, we'll complete chapter 3 and chapter 4 of the book Introduction to Reinforcement Learning by Sutton and Bartow. So I strongly advise you to practice the problems in chapter 3 and chapter 4. There are a lot of exercises in both these chapters. So you go home and practice these two chapters. Okay. So what is Q pi naught of S comma A? It's RSA plus V pi naught of S dash. So we are just approximating V pi naught of S dash as V naught. So it's V naught of S dash, right? The immediate reward plus the remaining reward. The immediate reward plus the remaining return. Okay. So this is the immediate reward that you'll get for taking action A, and this is the remaining return from wherever you go. Okay. Now this is the policy improvement step. And what is the policy evaluation step? So let's say we improved the policy and got pi 1 now. Then what will we do after this? We'll again evaluate pi 1, right? So what is the equation for evaluating pi 1? F pi of the previous v, right? So what is that? What is F pi? Okay. So this is the update rule, right? Bellman expectation update rule. So you have some vector v naught. Now you are applying the Bellman expectation on that. Correct? So now we'll keep repeating these two steps, right? You start with some arbitrary v naught and you just improve that. Okay. And then you evaluate it. And then just repeat these two steps. Okay. Here you are evaluating only for one step. Correct? And you keep repeating these things. So the only important point you have to notice here in the evaluation step, we are not starting with some arbitrary V naught and evaluating. We are using the previous V as our starting point. That's the only thing which we are taking care. Like in the policy evaluation, initial we have to start with some arbitrary V naught and use Vk plus 1 equal to F pi of Vk, right? So there, instead of starting with arbitrary V naught, since you are doing it only once, at least do it with the previous V that we have. Okay. Take the initial point as the previous V which we have. Okay. Yeah. Yeah. Everywhere the same algorithm, like you'll improve once, evaluate once. Uh, so in this step is done only for one iteration. That's what I mean. Instead of doing for uh, this many uh, things, we'll just do for once. Okay. Now, if you just look at these two equations carefully, if you apply the first one and immediately apply the second one, what these two expressions, if you together are equivalent to. So if you look at the first expression, here you are just finding argmax over A, and then that is giving you pi 1 of S. And after that, if you look at the second expression, it's like just substituting A equal to pi 1 of S, right? If you look at the second equation closely, if you look at this equation, it look like just like it's like substituting uh, pi 1 of S equal to like A equal to argmax of that, right? That's the only difference between these two equations. Correct? So that means both the equations together, I can write it like this, right? V pi of V1 of S equal to max over A, right? So I just calculated the argmax and I'm just substituting that into the same function again. So that means it's like max of that function, right? Is this clear? So I took argmax in the first step and just substituted that value in the second step. So effectively, it's like finding the max of the first thing. So this is equal to, what is this equation? Are you familiar with this equation? What is this equation? Bellman optimality equation, right? What if a vector satisfies Bellman optimality equation? What does it mean? If a V satisfies Bellman optimality equation, that means it's equal to V star, right? Any solution of Bellman optimality equation will give you V star. So if you just repeat this equation till Vk plus 1 becomes Vk, that means you will converge to V star, right? So I'll just write it. So just repeat this. So value iteration is essentially that you just do this. Okay. So this is the value iteration algorithm. Okay. Is this clear? So just applying policy improvement once and then doing policy evaluation just for one step. Both these updates together is equivalent to doing an iteration over this optimality equation. Okay. So this is essentially value iteration algorithm. You just repeatedly apply this equation. Like this equation is capturing both policy improvement and policy evaluation, everything. So you just apply this iteratively till Vk plus 1 is equal to Vk or however close you want them to be. Like you till Vk plus 1 is very close to Vk. Roughly we want Vk plus 1 equal to Vk. So you stick some small epsilon maybe and run it till Vk plus 1 is very close to Vk. Okay. So then you will converge to a very good approximation to our V star. Any doubts till this point? Are you understanding or you lost? So there are few. So similarly, this is also an iterative algorithm, right? This is like Vk plus 1 equal to some f of Vk. This is not f pi. This is some other f because there is no pi at all in the equation, right? In that equation, there is no dependence on pi. You just start with some arbitrary V naught and you just recursively apply this. So maybe this is Vk plus 1 equal to f of Vk, maybe some other f or g of Vk. Let's say. So if you want to show that this iteration will indeed converge, what should you show? Yeah, so what is that f we have to take? F is a mapping from Rn to Rn and f of, sorry, and what is f of V? Maths over A, RSA plus gamma times sigma S dash. I have to write this maybe in a vector form, but it's okay. V of S dash. Hmm. So this is F of V of S. This is the S part of that vector. Okay. So after applying F, this will be the S component of that vector, right? So this is what we have to take this F and show that this F is a contraction mapping. Okay. So I've written it in a scalar form, but you can just visualize it in a vector. Okay. Because if you remove those S's and just make it look like a vector, it will be in a vector form. So that is, it's, I'll not do that proof, but you understood roughly what you have to do, right? You have to just show that you take any 2 points before applying F and after applying F, you have to just measure the distances and you have to show that the distance decreases. In fact, we can show that the same gamma will apply here also. Like after applying F, the distance will be gamma times the distance before applying F. Just like how we have got for this thing. Here we got, right? After applying F, the distance is gamma times the distance before applying F. The claim is even for this F, you can show the same thing. After applying F, the distance will be gamma times the distance before applying F. So if that is true, then even this analysis will be true, right? This kind of analysis will work, right? Because here all that we used is the distance after applying F is gamma times the distance before applying F. We did not use any other properties here about F, right? The same proof will go through because Vk plus 1 limit will be V star there because as k tends to infinity, Vk tends to V star in that problem. So the distance between Vk plus 1 and V star can again be written just like this using triangle inequality. And if we can show this part, that the distance after applying F is less than or equal to gamma times the distance before applying F, then the rest of the proof will go through. So similarly, if you want to stop value iteration at some particular point, then you can use similar uh, stopping criteria. You fit some epsilon, you know the gamma, you just decide when you want to stop the value iteration. Okay. So the rest of the thing will be similar. Only the thing is you have to show that F is a contraction mapping with the factor gamma. Okay. So this is about the value iteration and policy iteration. Now we look at two variants, which are like small variations to these algorithms. So if you have, so if you let's say there is some variant called in place variant. Like these are all dynamic programming algorithms, right? As I mentioned before. So this is called an in-place DP variant, in-place DP variant, which is so if you want to implement our algorithm, let's say as a pseudo code, write as pseudo code. How will we write? We'll write like this, right? Let's say k is from 1 to, let's say you want to run it for some 10,000 time slots. Okay, let's say we are doing the value iteration coding. We'll write like this, right? You want to run for, let's say, 10,000 times, 10,000 iterations. And what will you do in each iteration? Every For every yes, you will just apply this update, right? For each, because you take Rn vector and output another Rn vector, right? We start with some arbitrary V naught, which is an n-dimensional vector, and we just apply this expression for each component of that vector, right? So for each S, we'll write this. Correct? This is how we'll implement, right? A value iteration algorithm. Now, this is called, this particular variant, this is standard way of implementing value iteration. So this is called synchronous way of implementing, in the sense that you are updating every S for every state you are updating in every iteration, right? In every iteration you are updating v of s for every s. So this is the standard way of doing it. So what does and you have to maintain two copies of this, right? Like this is like if you want to write it properly, this will be like v nu of s equal to maths over a rsa plus gamma right? You have some previous vector, n-dimensional vector. Now you are getting a new n-dimensional vector. Like if you have to maintain two copies of these vectors, right? In the code, you cannot just maintain one copy, right? Because for calculating every component, you need a lot of other components of the previous vector. Like you need v old of s dash for a lot of s dashes, right? To compute v new of s for a particular s. So you have to maintain two copies. So instead of maintaining two copies, if you just maintain only one copy, that's called in place DP. You just write it like this: V of s equal to, just remove V old and V new and just maintain one variable, one vector. So as soon as some V of s gets updated, you are using that in the update rule. You are not using V old of s to update. You're just maintaining one variable, one vector, and you're just writing the code like this. You just think of the code as this. Okay. So you just maintain one vector v in your memory and you just update like this. So this is called in-place dynamic programming, where you are using the latest values always. Okay. Any doubts in this? Anyone did not understand what I mean here? Fine. So this is called in-place DP. It is numerically observed that this has slightly better convergence properties. And there is something called asynchronous DP version. So here, no, like what does value iteration do? It will take, let's say I have two states, or let's say I have three states. Then my V naught will be, let's say, 1, 2, let's say 4. Let's say this is my V naught. Now, what will be my V1? Let's say, uh, like this depends on S to S dash, right? So let's say if I'm calculating for this s equal to 1. Let's say it has connections like, let's say this is non-zero for all the three cases. Like all the three states has some probability of going into S. Okay. So then what will my V1 depend on? V1 depends on these three values, right? Correct. So now I'll update the V1 based on these three values. Now let's say I get 2. Okay. Now when I'm updating this particular S, this, let's say this also has connections to all the three states. Now in this update rule, which when I have v naught of this particular one, whether I have to use 1 or 2 now. So that's the value iteration. If I use 2, that's called in-place DP. When I'm applying this update on this state, if I use this value, that's called in-place DP. If I use this value, that's called the standard way of implementing value iteration. I just said no, you're just maintaining one vector. So as soon as you do this equation, so you are having the same memory, so you'll just replace this one with 2, right? So that's the only difference. You're just always using the latest value by having only one memory, one vector. Okay. So asynchronous DP is, as I said here, if you have a large state space, In every iteration, you are updating the value of each state in this algorithm, right? You are updating the value of each state. So maybe let's think of some MDP where there are a lot of states. Let's say a chess game, it will have a lot of states, right? It will have a lot of states. So maybe a lot of such states are not may not be encountered. Like there might be a lot of cases, lot of states which you might not frequently encounter, right? If you have limited if you have limited compute power, you don't want to waste your compute power in updating some states which you most likely never see, right? Or maybe there'll be only few states which you'll encounter with very high probability in a game. So you don't want to keep updating your value and waste your compute on all the states that are possible in the game, right? Are you understanding what I mean? So because you might very likely encounter certain states. Some states you may not at all encounter. I very rarely you'll encounter. So if you have a very limited compute power, you want to put all your resources onto states which are most likely to be seen, right? So instead of updating every state in every iteration, you update only, let's say, few states or just one state, right? And that one state can keep changing over iteration. Like whatever you think right now is the most important state you should update, you update that state and just move away. Okay. So that's called asynchronous DP. Like the naive way of doing asynchronous DP is just arbitrarily sample one state from your state space and update that. That's a naive way of doing, just reducing the compute power. But there you are not taking care into which states are important, etc. Like how you do that depends on what kind of logic you want to use. But asynchronous DP essentially means that you don't update all the states in every iteration. You just update one state. How you choose that one state can result into various variants. So if I just choose that one state randomly, that will be giving me a random asynchronous DP. And some other way could be like every state, every you have, let's say, VK and VK plus, let's say you have VK minus 1 and VK. You have these two vectors, let's say. Now you want to find the VK plus 1. Now, if you go by the normal implementation, you will apply the update for every state in your VK, right? You'll apply this update rule for every state. Instead of that, you have the previous two iterates, let's say, with you. You just look at which component of these vectors are very far. Because when do you want to stop? You want to stop when VK plus 1 is closer to VK, right? So you just look at the difference between all these components of the previous two iterates which you have. Then see which has the highest error, right? Because you want to stop when these two components are closer to each other. So now just look at how much error is there in each of these components, and whichever state has the highest error, then you just update that particular state. Are you understanding what I'm saying? Because we want VK plus 1 to be closer to VK, that's when you want to stop. But some components might be already equal or very close. Some components might be, some components in this vector might be far away. You just apply the update rule. If you have to choose only one state to apply the update rule, choose the state which has the highest difference between VK and VK minus 1. Just apply, instead of applying for each S, you just choose that S which has the maximum difference and just update that particular state. Okay. So that's called prioritized DP. You are prioritizing the states which have large errors. Okay. Like asynchronous DP, just update one step, one state. So how you choose that one state will lead you to different variants. So one way is randomly choose that one state. Like that is one variant. Another variant is you update the state, update S with Which state has the highest error? Okay. So you look at the previous two iterations of your value iteration and see which component of V case has the highest error. You just update that S in your current step. Okay. So this is called prioritize PP. Yeah, so that is just I'm just telling to for the sake of explaining that particular thing. That's just it. I'm just telling what do we mean by updating only one state, just to understand that arbitrarily choose or randomly choose. That's a trivial way. The like this might not be a useful way of doing it. Like it might not just increase the value, but it might uh, update the same state again and again also, right? So it's not the same as doing value iteration. If the same states get selected for a few successive iterations, so the update will be different compared to what the previous update is. So, but you have to do it in a meaningful way. Like this is one way of doing it. You just look at the error and whichever component has the highest error, you prioritize that state to be updated. Okay. And now, so this is all about. This is all that we'll cover about how to solve the optimal policy when the dynamics of the MDP are known. Okay. If you know the dynamics of the MDP, that is, if you know RSA and PSS dash A, these are the algorithms that you can use for value iteration and policy iteration and few variants of them. Now, the main interest is when you do not know the dynamics of the MDP, how do we deal with it? Okay. So, in practice, for a lot of useful applications, we do not know these dynamics. So, let's say you're training let's say you're training a small robot to walk or something. You don't know what exactly if you bend in some particular angle, you don't know exactly where you will fall. Like what state will you go into with what probability. You have to just try that and see what happens. You want to let's say lift an arm, you just press that action and see where what will happen. You cannot exactly have the model of what happens if you press that particular thing. So you have to just try out different things and see what happens, and based on that, you have to decide what is a good policy. So that's the main model tree RL part. You do not have the dynamics. That is, you don't have any idea on which action is good or which action will lead you to what state. You have to learn these things by interacting with the environment. You just try some action. The environment will give you a new state and a new reward. Based on that, you learn whatever you want to learn. Okay. So the cost is about how many episodes of interaction you want with the environment, right? So that's the learning thing which you'll have. Okay. So, so let's get into model free. So when I mean model free, we do not know. So by dynamics, I mean RSA and PSSS. We do not know these things. Okay. We don't know these things. And if you don't know these things, we cannot apply value iteration, right? Because in value iteration, in that F, we need these things, right? You need RSA, you need PSS dash A to apply value iteration. But if you don't know these things, we cannot apply value iteration, right? So that means our current algorithm will not help us in this model free setting. Okay. So now what, like there are, so just like how we have done in the policy iteration, roughly what did we do in policy iteration? We started with some policy pi naught. We understood what is the value of that policy. then we improve that policy, right? So there are mainly two steps. Like for a given policy, you want to understand how good is that policy. That's one step. So that's generally called as a prediction problem. Like if you have a policy, like you decided some policy, you want to understand how good is that policy. Okay. So that problem is called as a prediction problem, predicting V pi for a given pi. Okay. So we call that as prediction problem. Prediction is given pi, estimate V pi. So that is the prediction problem. The other problem is referred to as control problem, which is find pi star. Okay. So the control problem is called as is like finding optimal policy is referred to as control as to deciding what actions to take. That's the aim. So how to control the agent, what actions to take, what policy we should use. That's what is called as the control problem. That is finding pi star. The prediction problem is someone has given you a policy to use. You want to just understand, estimate how good is that policy. That's called the estimation problem, like prediction problem. So to begin with, we'll do the prediction thing. So we are given, someone gave us some policy pi. In what state, what actions you have to take is given to us, but we don't know the dynamics. Okay, but you have yeah, access to the environment. That is, you can try some action and you can see what happens. Okay, so uh, so you are in some state. Yes, you can take whatever action you want. Then the environment will give you ST plus one and RT plus one, right? So can someone tell me what is at least some naive way of uh, some simple way of finding V pi of S? I give you the policy. I give you the ability to interact with the environment. Okay, you can start with whatever state you want, and then you can take whatever action you want. The environment will give you a new state and action. You can keep doing that. You can interact with the environment. So you can do whatever you want, and I want you to estimate V pi of S. Okay. So can someone suggest a simple algorithm, a simple way to do that? What is V pi of S? What is the meaning of V pi of S? This is like the discounted expected return, right? So what is return? Sum of rewards till you reach end of the episode. So can't you think of a simple way to find V pi of S? Estimate V pi of S? Yeah, you keep playing according to pi and interact with the environment, keep playing according to pi. And then what? Huh? Okay. So let's say you start with some status and let's say S not equal to S. We started with or some at some t you reach some status, let's say. Then you keep interacting with the environment according to pi of S. You take this action pi of S. Then the environment will give you ST plus 1 and RT plus 1, right? Then you again take action according to pi and you keep doing this till you reach a terminal state. Then what is a estimate of V pi of S? Like GT, right? GT is RT plus 1 plus gamma RT plus 2 plus so. Okay. You just calculate these things. You just calculate this value from your episode of interaction. So you just interact with the environment till terminal state arises. And just, you are observing these rewards, right? Environment is giving you these rewards. You just look at the sample rewards that you got and just calculate this value GT, which is the return that you got, RT plus 1 plus gamma times RT plus 2, gamma square, RT plus 3. So now you got one sample of, like, expected GT is nothing but V pi of S, right? Because you started in state S and you got one sample of the return. Expect V pi of S is nothing but expected GT, right? So you just do one episode of interaction, you get one sample for V pi of S. So after this, you store this value. Maybe you again start with state S and again interact till you reach the end of the episode. You collect one more sample of GT. So let's say you collect some 10 times or whatever. You do this some number of times. You get several samples of GT. You just take the average of all of them. What will that be? An estimate of V pi of S, right? You start from status multiple times and you interact with the environment till you reach the end of the episode. Just take the average of those returns that you get. So that will give you V pi of S. S is some state. No, if you want the V pi of S for lot of states, you have to just do this for lot of states. So, like, if you measure the GT from state S, that will give you an estimate of V pi of S. Let's say ST plus 1 equal to S dash. If you look at the GT plus 1, that will give you a sample estimate of V pi of S dash. Right? If you look at the return starting from this place, you'll get an estimate of V pi of S dash. Right? So in this episode, you'll get a lot of estimates. Correct? For every state, like if S dash is this is the first time S dash came, then if you measure the return from that state, you'll get an estimate for V pi of S dash. Okay. So uh, there are two variants in this Monte. This is called Monte Carlo method. So this is called Monte Carlo prediction method. So one interesting thing is, let's say you start with some status. Uh, is it guaranteed that in that episode you'll never visit S again? So you started from some status and you are interacting with the environment. Let's say the terminal state has not yet arisen. Will you see S only once in that episode or multiple times you could reach S? Multiple times we can reach S, right? So then what should I take as V pi of S, estimate of V pi of S? So let's say I am at, I started with some state ST equal to S, but let's say ST plus 2, again I came to state S. At ST plus 2, again I came to state S. Maybe at ST plus 10 also I again came to state S. Now I have three places where S is there. So then what should I do? Or what should I take as my estimate for V pi of S? Okay, so one of you are saying that take three samples. Why do you want to decide which sample to take? Why don't you take all the three samples? Because all three samples are starting from S and giving a uh, sample for GT, right? So that's called every visit Monte Carlo. That particular way of doing it is called every visit Monte Carlo. You just collect all the GTs wherever you. If you encounter S, you look at the remaining return. You take that as an estimate for V pi of S. And there is a, if you take only the first visit as the estimate, that's called first visit Monte Carlo. So you started with status. Let's say at ST plus 2, you again reach status, but you will not take this sample for your calculation. You'll just only take this sample for your calculation. So this is called Monte Carlo first visit algorithm. Okay. So one minor technicality is if you encounter the status multiple times, these are not independent samples of GT. Like the first sample and the second sample has a lot of correlation, right? The GT that you get for the first sample and the GT that you get for the second sample are differed by only RT plus 1, right? So there is a lot of correlations. So these are not independent samples of your GT. So there will be some bias in your algorithm. but it will help you converge faster. So like there is no clear, uh, like empirically it's not very clear which is a good strategy, but both these are used. In some cases you see the first one doing better. In some cases you see the every visit algorithm is doing better. But these are just two variants. Okay. So in so this is about Monte Carlo prediction. In There is another algorithm called temporal difference algorithm, which we'll look at in the next class. Thank you.